Welcome to the quiz key. So let's look at the first question. This one's pretty straightforward. The orbital type is just determined by the shape. So looking at this dumbbell shape, we know this has to be a p orbital. Anyway, nothing more to say about that one. All right, what about this? How many p orbitals are there for a given value of n? Well, if we think about p orbitals, how could we approach this question? Well, remember that a p orbital means that L is equal to 1. Remember that S, P, D, and F are just codes that tell us how big the quantum number L is. So if L is equal to 1, what does that imply for M sub L? How many different values could M sub L have? So M sub L varies from negative L to positive L in steps of 1, going all the way through 0. So the set of numbers that M sub L could be, let's make this an M sub L. So what could M sub L be equal to? M sub L could be equal to any one of these numbers. It could be negative 1, it could be 0, or it could be positive 1. All of those are good possible values for M sub L given that L is equal to 1. And we know L is equal to 1 because we're talking about a p orbital. And that's true for any p orbital, whether we're talking about a 2p, a 3p, or 4p, or whatever. Okay, so any set of p orbitals, there's going to be one that's got an ml of negative 1, one that's got an ml of 0, one's got an ml of positive 1. So that means there's always going to be 3 different p orbitals for any level. So there's 3 different 2p orbitals, there's 3 different 3p orbitals, there's 3 different 4p orbitals, etc. So for any given value of n, there's going to be 3. So the right answer has to be this. It has to be 3. And remember, ml gives you the direction of the orbitals. So every p orbital looks like a set of dumbbells, but you can imagine a set of dumbbells pointing along the x-axis, the y-axis, or the z-axis. So that's 3 different ways of pointing. We've got 3 different orbitals, 3 different values of M sub L. Okay, so enough about that one. The question asks how many electrons could be put into the orbital depicted. Actually, it's even simpler than that. For any orbital, it doesn't matter which one, it's always going to be, we can only put 2 electrons in there. And that's because of the Pauli exclusion principle. Okay, so Pauli exclusion principle, unlike Aufbau and the Hund's rule, doesn't just give you the lowest energy state, it tells you what's possible or impossible. So it's impossible to put 2 electrons into a situation where they have identical sets of quantum numbers. So once you've chosen an orbital, you've chosen n, you've chosen L, and if it's a specific orbital, you've chosen ML. So the only way to have the electrons have different sets of quantum numbers is if they have different values of n sub s. And there's only 2 possible values of n sub s. One is plus a half, and the other one is minus 1/2. That was a typo. This is minus 1/2 and plus 1/2. So once you've got 2 electrons in an orbital and you try to put a third one in, if you put its spin up, plus 1/2, it's going to match that first electron. If you put its spin minus a half, it's going to match the other. You can't do that. So that's why there's only room for 2 electrons in an orbital. It's supposed to be m sub s. So let me copy that just so that the text looks right. Okay. And so the answer has to be 2. What electron configuration is impossible? Actually, this is the same reasoning as the one we just discussed, because we've got 3 different p orbitals at the 2 levels. So there's a 2px, 2py, and 2p. So if there's 3 different orbitals, each orbital can take 2 electrons. That's 6. So we can't have 7 electrons in a set of p orbitals. Okay, what about this one? Ground state for nitrogen. So if we look at this, all of these have 1s2. That's good. All of these, most of these have 2s2. This one doesn't. If we look at a periodic table, we can see the total number of electrons for nitrogen should be equal to 7. So we've got, we look at these down here, we've got 2, we've got 4, 7, so this matches. This matches. This actually adds to 7 too. This is just too many electrons up here, so let's look down at these. If we look at these, something's funny here. We've not filled up this level before we moved up to this one, so that violates Aufbau. So this is a possible electron configuration, but it's not the lowest energy. So let's put a little notation on here that this is possible, but not ground state. Because we filled in the 2p before the 2s, and we put electrons in 2p before we filled up the 2s, and the 2p is higher than the 2s. So now let's look at these two down here. What's different about them? Well, here it looks like we skipped over the 2p level entirely. So once again, that's possible, but it's not ground state. That would be, you have to put a lot of energy into the atom to do that. That would be an excited state, because we've taken all these electrons in 2p and put them in a 2,3. And here, this is actually the ground state. So let's go ahead and underline this. Okay, so this one and this one, choices B and D, violate Aufbau, which means they're not the ground state. They're not the lowest energy state, but they're still possible. But this one would violate the Pauli exclusion principle. So let's go ahead and write that in. Okay, so this is the right answer. Now getting down to the last multiple choice question, electron in a 3p orbital, what's the value for L? So the key thing here is not the 3, it's the p, because p is the code that tells us what the value of L is. So right away, we know I'm going to go ahead and underline this. That's what tells us the value of L, and the code is S is equal to L equals 0, and P is equal to L equal 1. So let's go ahead and underline this. So that's just the SPDF code that you need to make sure you've learned that. Okay, so that's the key for the first half. Let's do the second half now.